A couple of different items. Number one, not only did you get 5 points for the homework, but I went ahead and gave you 10 points for the quiz that would have been today. So just letting you know there's no quiz tonight or homework tonight, due tonight. Number two, there is an opportunity, if you are available between 9 and 11 at least, to go to the STEM career fair. And if you go to the STEM career fair and sign in, then they're going to give you a certificate that you were there that you can bring to me, and that's an opportunity to earn 5 bonus points for just going. That would be added at the end of the semester. So just like the conversations with chemists was up to 10 points, this is another way to earn some bonus. And I made that announcement today.
I just asked what day it is.
I believe it's Wednesday of this. I don't know if it's this week or next week.
It's October 9th.
Okay, so next week. Thank you.
Where's it at?
It's in the Student Center ballroom. There are signs for it. I just, and I can give you more information. I just saw it in an email and thought I would offer it up as an opportunity. How many bonus points earned home? Starting, I think it is. I can't remember if it's 25 or 30. I'd have to look at what I said in the thing at the beginning. But other questions? Okay. There are no other questions, then I am going to go ahead and get started into today's information. Today, what we are talking about so I introduced the last chapter with the fact that that was a chapter that was going to discuss the speed of the reaction. How fast will a reaction occur? For the next 3 chapters, we will be discussing to what extent does a reaction occur. And then after that, we will get to the question, does the reaction occur in the first place? So In college chemistry 1, when we wrote a reaction, such as, oh, let's just take the reaction for the burning of octane. We always wrote the reaction with a single-headed arrow. That single-headed arrow is basically telling you that this reaction goes to completion. The single-headed arrow basically is telling you that this reaction goes to completion. Meaning that the reactants are completely used up on their way to making product. Now, this is true for some reactions. It's true for strong acids dissociating in water. It's true for soluble ionic compounds dissociating in water. It's true for a variety of reactions. But there are a lot of reactions that do not go to completion, such as when you add a weak acid into water. A weak acid does not dissociate entirely in water. Instead, it sets up a dynamic equilibrium. I alluded to a dynamic equilibrium when we first started talking about rates of reactions. In that, if you think about the concentration versus time of a reaction, you start out with a lot of reactant. Initially, the reaction is going to go rather rapidly from reactant into product. And the reactants are going to get used up. And this makes sense if you think of collision theory. For the reactants to react to form products, they have to collide. Well, when you have a ton of reactant present, it's easy for those reactants to collide with one another. But as the concentration of the reactant decreases, the likelihood of those reactants colliding becomes much less. In the opposite, you have product. Initially, there is no product. So as those reactants are combining, it's easily going to form product. But at some point, the product concentration will level off, and you obtain what's called a dynamic equilibrium. Essentially, what happens when you obtain a dynamic equilibrium is the reactants will go to form product as fast as the product goes to form reactants. So it appears as if the concentrations of the reactants and the products, well, excuse me, the concentration of the reactants and the concentration of the products no longer change. It appears as if the reaction itself ceases to run, but that's not truly what happens. You constantly will have these reactants combining to form products, but it's going to occur at the same speed as the products recombining to form reactants. And you set up a dynamic equilibrium. We represent an equilibrium reaction with a double-headed arrow. Now, most of the time, you're going to see me draw the arrow with this type of format, where you have half of an arrow pointing in one direction and half of an arrow pointing in the other direction. Sometimes you're going to see it written with just a double-headed arrow. It all depends upon ease of the word program and what we can find. It's sometimes harder to find those equilibrium arrows, but this is the more common form of an equilibrium arrow. So for example, I mentioned a weak acid. Let's take acetic acid. When you toss acetic acid in water, because it is a weak acid, it only partially dissociates, and it winds up setting up an equilibrium between the reactants and the products. So once again, let's talk about what's going on if you have a reaction at equilibrium. Number one, it appears as if the reaction has stopped, but that is not the truth. What is actually occurring is that the reactants are going to make a product at the exact same rate as the product is going to make reactant. So the rate of the forward reaction is equivalent to the rate of the reverse reaction. The concentrations of the reactants and the concentrations of the products stop changing. Again, it doesn't mean that the reaction has stopped. It just means that you've got reactants, you've got some in flux on their way to product, but as quickly you have some of the product in flux on the way back to the reactant. So it just appears as if the concentrations have stopped because they're not changing, but it doesn't mean the reaction has stopped. Yes.
Do you ever like calm down? Does it ever like relax, or does the reaction like constantly?
There is probably, it probably depends on the outside influences. So if I'm constantly stirring, you can guarantee that the reaction is constantly going. And in reality, we can't see it, but the reaction is pretty much constantly changing, constantly in flux.
Okay. So we can write an equilibrium expression and set that equilibrium expression equal to an equilibrium constant. Let's talk about the equilibrium constant first. The equilibrium constant is represented with a capital K. This is to differentiate it from the rate constant. It is represented with a capital K. Now, you may see the equilibrium constant written in a variety of forms. K subscript C means that you're talking about a concentration equilibrium constant. K subscript P means you're talking about a pressure equilibrium constant. Some others that we will see include K subscript A, which means we're talking about an acid dissociation constant. We may see KB, that is a base dissociation constant. And another one that we will encounter is KW. That is the equilibrium constant for water. And I think the last one that we will encounter is KSP, which is the solubility product constant. This one is specifically associated with your insoluble ionic compounds. So basically, if you see a capital K, you're dealing with an equilibrium constant. What is the meaning of the equilibrium constant? Basically, the equilibrium constant tells you to what extent a reaction occurs. So if we think about a number line, we have the value of 1. The more positive the number, the further the reaction goes to equilibrium or goes to the products. Whereas if you have 10 to the negative numbers, that means that the reaction pretty much doesn't occur. To any great extent. Example, hydrochloric acid, which is what we know as a strong acid, When you add a hydrochloric acid to water, it pretty much goes to completion to make hydronium and chloride. The reason we know that this goes to completion is because this has a K value. This reaction has a K value along the lines of 1 × 10⁶. So it is a very large equilibrium constant, which means that the reaction pretty much goes to completion. Compare that with our acetic acid. In water. And that really does set up an equilibrium. With a value of about 1.8 × 10⁻⁵. So what that tells me is that there is a lot more reactant present than there is product for that equilibrium equation. So that the equilibrium constant is represented with a capital K. It tells us to what extent the reaction has gone to form products. The larger the value, the more products you have in solution. The lower the value, the less product you have in solution. The lower the value, the more reactant you have in solution. Yes.
How did you get that number?
I have them memorized. You will not be expected to have them memorized. You will be given the numbers if you just need to understand what they mean. Yes.
So like, that one's an equilibrium. So what would like the developing fast be then?
If it's 1, you have pretty much equivalent reactant and product.
Okay.
Yes,
So if it's a negative exponent, it means it's going to be more for the reaction side.
correct. Correct. Okay, so that is the equilibrium constant. Now we're going to talk about an equilibrium expression. Number 1, an equilibrium expression is said equal to the equilibrium constant. The equilibrium expression is going to be the products raised to their coefficient divided by the reactants raised to their coefficient. The third thing about an equilibrium expression is that the expression only includes states of matter that are likely to change. Or I should say likely to have significant changes. What that means is that we will only include gases and aqueous compounds in our expressions. So let's look at some examples. This is the real reason I brought my textbook with me, so I don't have to make them up. Okay, let's take CO2 gas plus 2H2 gas goes to form CH3OH gas. And let's write an equilibrium expression for this reaction. First of all, the equilibrium expression will be equal to the equilibrium constant. It will be the products raised to their coefficient. So in this case, CH3OH raised to the 1, divided by the reactants multiplied together, raised to their coefficient. So CO2 and the hydrogen would be raised to the power of 2. Let's take another reaction. N2 gas plus 3H2 gas goes to form 2NH3 gas. Again, the equilibrium expression is set equal to the equilibrium constant. And it is the products raised to their coefficient. So NH3 raised to the power of 2, divided by the reactants raised to their coefficient. So N2 is raised to the 1 and H2 is raised to the 3. Let's look at this one. 2KClO3 solid goes to form 2KCl solid plus 3O2 gas. The equilibrium constant is going to be the products raised to their coefficient. Now, in this particular case, we are only going to include the oxygen because we only include gases and aqueous. So the equilibrium expression is going to be the O2 raised to the 3rd power all over 1, or in other words, just it can be written as O2 to the third power. Questions? Okay. Any questions about writing an equilibrium expression or what dynamic equilibrium means? Well, then we are going to talk about the relationship between the equilibrium constant and the chemical equation. To do so, we're going to use the generic equation. A plus 2B goes to form 3C. The forward reaction, the K for the forward reaction, is going to be equal to C cubed all over A times B squared. Now, excuse me. If I were to write this in reverse, 3C goes to form A plus 2B. The K for this reverse reaction is going to be equal to A times B squared all over C cubed. Now, if you look at this is the inverse to the forward reaction. So what that means is that the K for the reverse can be determined as 1 over the K for the forward. This is something you're going to need to know. and be prepared to work with. I will do a couple of problems. I may not get to them today. They may be the start of Wednesday's lecture. But you need to be prepared to work with that. Let's go back to our original equation here. A plus 2B goes to form 3C. And our original equilibrium expression of, which is C cubed over A times B squared. Well, let's alter this reaction and make it 3A plus 6B goes to form 9C. The equilibrium expression for this one would be C to the 9 divided by A to the 3, B to the 6. If you compare these two, what you will notice is that they have been raised. The initial K expression is raised to the power that the second equation was multiplied by. Meaning we would have gotten the same thing if we'd have taken K, our original K of C cubed over A times B squared, and we would have cubed everything there. So we can write a new expression, another one that you should become familiar with, which is K prime is equal to K raised to a power. That power being the multiplicative for the reaction. Questions so far? So basically all we have stated is we've discussed dynamic equilibrium and what it means. We've discussed equilibrium constant and what the equilibrium constant means with respect to the amount of reactants and the amount of products present. We have talked about how to write an equilibrium expression, where that equilibrium expression is equal to that equilibrium constant. And now what we have done is we have talked about if you flip a reaction to get the new equilibrium constant, the new equilibrium constant is 1 over the original equilibrium constant. Or if you multiply a reaction by some coefficient, the new equilibrium constant is equal to the old equilibrium constant raised to that coefficient. There is one more manipulation that we're going to talk about. And that is, let's look at the equation, the reaction A goes to form 2B, and 2B goes to form 3C. In other words, let's look at a reaction mechanism. We can write an equilibrium expression for each of these. The equilibrium expression for the first one is that K is equal to B squared over A. The equilibrium expression for the second one is that C cubed is C cubed over B squared. And I'm going to call it K1 and K2 just to keep them straight. Now, if we were to add the reactions, together, we would have A plus 2B goes to form 2B plus 3C. And you would see that this equilibrium constant for this third reaction is C cubed B squared all over A times B squared. And since B is the same thing, it cancels out. That works. So it becomes K3 is C cubed over A. Now, we could have gotten to K3 by taking K1 and multiplying it by K2, and that would have equaled K3. We can prove that because B squared over A times C cubed over B squared. The B squareds are going to cancel out, and you're left with C cubed over A. So let me just take this last piece, which I know is a lot of proofs, and break it down into the simple, straightforward. You reverse a reaction. Your new K, which I'm going to call it K prime, is going to be equal to 1 over the original equilibrium constant. If you multiply a reaction by a coefficient, your K prime, your new K, is going to equal the original K raised to that coefficient. And finally, if you add reactions, then the new K, K prime, is going to equal the K for the first reaction times the K for the second reaction, and so on and so forth. That's what it boiled down to. This is the key. This is what you need to know of the last little bit of what I've done. So let's look at examples. And I will start with this, but I will finish with this too. I mean, basically we will have to do more of this on Wednesday. Thank you. Okay, let's look at we're going to start with going a little crazy, I suppose. Two COF2 gas goes to make CO2 gas plus CF4 gas. This has an equilibrium constant of 2.2 times 10 to the 6th. I want to know the equilibrium constant of 2 carbon dioxide gas goes to form 2 carbon dioxide gas plus 2 CF4 gas goes to form 4 COF2 gas. Basically, folks, what you got to do is you got to ask yourself, what's going on here? Number one, I reversed the reaction. And number two, I multiplied it by 2. So my K prime is going to be the reverse, so 1 over K. And since I multiplied it by 2, it's also going to be squared. So that's going to be 1 over 2.2 times 10 to the 6th squared. Which comes out to be 2.07 times 10 to the negative 13. Yes.
Can you, So because it was reversed, you did the 1 over K2, because it's multiplied by 2, that was the second step.
Right. That's why it was K to the power. Questions? Okay, we're going to pick up with a few more examples of this. And then we're going to move on to the fact that I said you could do KC, which is mainly what I've been talking about, but you can do KP, and we're going to talk pressure and equilibrium constants. And then we're going to talk about how to shift between them on Wednesday.